Hey guys, how's it going? So today actually we're gonna be taking a look at LoRa. So as usual, we're gonna go through the source code, we're gonna go through the paper, and we're gonna write the pseudocode and commit just to keep you guys updated how far we are. So we started with the model, like the pre-training model and all the best practices, all the components that are required to pre-train LLMs. So this required us to talk about things such as root mean squared layer normalization, the rope encodings, why we needed flash attention, and why we're using it this way. Based on the PyTorch 2.0 optimizations kernels. Then we spoke about the quantizations. So I made the paper on the quantization, the GPTQ algorithm, including the paper. We covered the sparse GPT. So I wrote this sparse GPT. However, I did not commit to the Lightning team. So yeah, for now, if you want to go through this code of sparse GPT, you can find it in my repo. So yeah, that would be cool. Then what's left is LoRa and adapters. So that's what today we're gonna look into. We're gonna look into LoRa. Then after we're done, we can look into the adapters. So without wasting any time, let's get into it. So the core idea behind LoRa is that it freezes the pre-trained model weights and it injects trainable rank decomposition matrices into each layer of the transform architecture. So this is greatly going to reduce the number of parameters required for us to fine tune. So how it reduce the number of parameters required for fine tuning because of we are freezing the pre-trained model weights, so we don't need to necessarily make any updates to these freezed weights. So the only thing that we need to update or optimize is these rank decomposition matrices, right? For you to better understand this, let's look into how we will do what we call full fine tuning, right? So if we have like weights here, we can think of this as like the weights of GPT-3, that's okay. And we have the input, we're going to have a forward pass and we get the output like so. Then during the propagation, we're going to have to compute the gradients and we need to update these weights, right? But the problem with this architecture or doing it this way is that we're gonna need the same parameters as the weight. So if like, for instance, GPT-3 has 175 billion parameters, we're gonna need the same number of parameters for us to update these weights, right? Not only it becomes a bottleneck for us to fine tune, but also because of when we fine tune these models so that they can fit in different environment, whether it's medicine, whether it's law, then storing and deploying these many instances of fine tune model can become really, really painful. Okay, now you might be like, I do get it. So the pre-trained weight is going to be freezed, and the only thing that we just need to optimize is these decomposition rank matrices. But also, you might be asking yourself, are these decomposition matrices not going to add some sort of like a bottleneck? So what they did, the authors, is to look back and they found out that actually previous authors said that the parameters of the model can be represented in what they call low intrinsic dimension. So what this means is that the length over parameterized model also exists in low dimensional space despite having large number of parameters. So these rank decomposition matrices can actually be as small as 0.01% percent of the pre-trained weight. So they can be quite small. Hence, you can you can fine-tune your model using the LoRa technique in an efficient way. And this is because we also do not calculate the gradients or maintain the optimizer states for the pre-trained weight. So instead, we only need to optimize the injected low rank matrices, which can be as 0.01% of the pre-trained weight. So they can be quite small, right? So how this will work from a high level perspective is that you're going to have the input, right? And you're going to pass them within these pretrained weights, and you're going to also pass them within these rank decomposition matrices, and you're going to have to add them up, and that's what you're going to do. Then when we are done to update the pre-trained weights, you're just going to add these decomposition matrices to these pre-trained weights. I'm going to get into that, but I'm just trying to juggle your mind by giving you the high level of LoRa architecture. Okay, So with the full fine-tuned technique is that we are trying to find the optimal values of the pre-trained weights. How we do this is that we're going to find the probability of predicting the next token using the pre-trained weight given the input and also the partial output, because of these are autoregressive models. But instead of doing it this way, what do we do using the LoRA technique? Our objective now becomes that we want to find the optimal value for the parameters of these small size matrices that we spoke about. So we're still doing the same thing. It's just that this here we add these updates of these small size matrices, right? So these are all these what we call rank decomposition matrices that we spoke about. So we add these to these freezed parameters of the pre-trained weights, right? So that's what this means. So the weights update are going to be represented by the update from the decomposition matrices, which is B and A. So these decomposition matrices will be having the dimension of D by R and R by K. So yeah, like I showed you, is that you can think of this as like D, then we have R, then we have R, then we have K, like so. Okay, so it's the same diagram that I showed you when we started. So this R here is going to be a hyperparameter that we can select. So it can be less than, it can be, it has to be the less than the minimum of D by K. And also this is a hyperparameter, like I said. So it depends on the value that you selected, but you just need to play with it. But I think I read somewhere within this paper, they said that if you select a very, very small, then the model might not capture like more information. But if you select like a very large, then you might increase more parameters. So it's more like you have to play with it and see which one is the right number, so to speak, right? So yeah, I'm gonna write a pseudocode so you'll definitely understand how it works. Anyway, um, the input here, the we're gonna be this input is gonna be passed through the pre-trained model, which is frozen, and also these are decomposition matrices respectively. Then the output from these two will be added, will be summed, right? So what they say that the output vector are summed coordinate wise. That's what the paper says, right? So that's that. Then another nitty gritty is that we need to initialize these matrices. The first matrix, which is A, is going to be initialized with random Gaussian. Then the second one is going to be initialized with zeros. This is because we want to ensure that the weight update of B and A is at zero at the beginning of training. That's what the author state. Okay, so yeah. Anyway, that's like all it is to this. I think going down is going to be about the results and the empirical experiments. So yeah, I'm not going to cover this, but what I'd like to do is that I would like to cover the pseudocode so that we get to solidify our understanding. If you don't want to watch the pseudocode, then you can just skip and go straight to Lightning, where we look into the source implementation of the Lightning project for Llama, for LoRA code. So coming to our pseudocode, what we have is that we have our pre-trained model, which is frozen, and we're just going to take the dimensions of this model, which is going to be the input size and the output size. This is mainly because we want to initialize our decomposition rank matrices. So the B is going to be input size projected to rank hyperparameter value. Similarly, A is going to be rank to output size. Okay, so we need to make sure that the weight updates of these two matrices are zero at the beginning of the training. So what we do is that we go into make sure that the B matrix is initialized to touch dot zeros, whereas A is going to be initialized to random Gaussian. Okay. Then that's that. What we need to do now is that we need to pass the input to the pre-trained model, and we also need to pass the input to this decomposition rank matrices by doing a matrix multiplication between these two matrices with the input, right? So the only thing that's missing here, and which I forgot to mention in the paper, is that we need to multiply this by the alpha. So essentially, the alpha is the scaling factor that is going to adjust the magnitude of the results. So in a more intuitive way, it helps us to balance the pre-trained knowledge model. So with the adaptation specific task. So what we need to do is that we need to pass this alpha also here, right? So this is gonna be one by default. Just gonna make sure that I say this is gonna be model self dot alpha, which is going to be alpha like so. Then I just need to make sure that I call this self dot alpha and we should be fine. Sorry, and that's that. Then if you still remember from the paper, what we did was that we needed to add the output of the from the model, right, and the output from this rank matrix multiplication. We add them together and we're going to return the output, right? That's what we did. So that's that. So the only thing that I need to make sure is that I'm going to assign the alpha because I pushed this code to the repo. So just going to make sure that I write something that people can understand. So as you can see, it's quite easy, and we didn't even spend a lot of time because of that's all it is to this, right? We just add these two matrices, and what we do is that as we train, we just gonna be updating these, and these model weights are gonna be frozen. We just want the output, and we're just gonna be taking uh, we're gonna be updating the weight of these, optimizing the weight of these two matrices, right? So that's all it is to this. I know it was short than usual, but anyway, let's get into the source code and see actually how it plays out in a large scale transform model like Llama. So coming to the source code of Lightning Llama, so within this folder here called Lit-Llama, we have this file called LoRa.py. So this file here is going to be holding the core logic behind LoRa. So what we just explained now in the paper and in the pseudocode is going to be done within this folder, right? Then the fine tuning itself, like whereby we need to get the data, like the pre-trained model, it's going to be done within this folder called fine tune, and you're going to find this file called LoRa.py. So this is where the training is going to be taking place. So we're going to start with this file because I feel like they are dependent on one another and we shall cover them in a sequential way. So we're going to start with this, then we're going to go to the second file when we're done. Okay. So what we have here, we have this class called the LoRa layer, in which we're going to initialize these parameters that we covered. So this is going to be the rank, and we have this LoRa alpha, which is the scaling factor that is going to adjust the magnitude of the results that is coming from the pre-trained model and the LoRa weight. So what I mean here is that sometimes you can fine tune, right? But then the the pre-trained model can still overshadow LoRa weight. So in this case, you might want to increase the LoRa alpha, but also the LoRa alpha might overshadow the pre-trained weights. It might not have a lot of impact. So that's why we say that it adjusts the magnitude of the combined results. So it balances the knowledge between LoRa matrices and the pre-trained model knowledge. So that's what this means. Then you have this LoRa drop route, which will be applied on the first matrix of A. We're going to get into that a little bit. Then we have this match weight. So how you can think about this is that not all the time when we have an input, we're going to be we can actually multiply the input with the meshed weights. So by meshed weights, I mean these pre-trained weights have been meshed with LoRa matrices, right? So it's one thing. So if they are not meshed, then we have to perform the merging step. So hence this is a boolean which is going to be true or false. Then if like it's false, then we know we have to match those matrices with the weights. Okay, so we're going to also look into that in a second. So that's that. We have this meshed linear class. So this input and output features are going to be representing the input features of the pre-trained weight as well as the output features of the pre-trained weight. Then these hyperparameters are the ones that we just explained right here. Then we have this enable LoRa. So this is going to be quite important because within the attention mechanism, we have query, key, and value, but we do not want to apply a LoRa probably on all of these three matrices. So what we do is that we're going to have a list of Boolean which will tell us if which of those we want to apply LoRa on, right? So it's going to be holding three values like so. Then we have this fan in and fan out, which is also going to be bool. Then we have this match weight. Like I explained, this will be true or false because it's going to tell us if like we should be, if the weights are already matched or they are not. So we're going to get into that and you'll see how it actually works. Then we have this code here in which we're going to be initializing our LoRa matrices. I hope you still remember these A and B as shown in the code. But what we have here is that we're going to be having this rank, which is going to be multiplied by this enable LoRa. So how you can think about this is that enable LoRa is going to be having three values, and those three values they represent if we want to apply LoRa on query, key, or value. So for instance, I think the best way to understand is if we make an example. So how we can think about this is that actually I'm just gonna, let's say we have we're gonna say R, which is gonna be 2. Then we're gonna say this is gonna be the rank hyperparameter. Then we can say okay, enable LoRa is gonna be this is going to be a list of boolean. So this is going to be true, false, and it's going to be true. Then we can probably say the input features, right? The input features is going to be equals to 128, right? Then the output features is going to be what is it, 128 by 3. This is going to give us 384, right? If I'm not mistaken. Yeah. And what we have here is that we're going to be summing this list. So this is gonna give us 2, right? We multiply this r, which is currently 2. So this is gonna give us 4 all in all. So I'm just gonna write this dimension here 4 because we multiply this by 2, which is this 2 is coming from these two true, right? Meaning that probably we want to apply LoRa only on query and key, not on value. So you can think of it that way. Then we have this input features, which is going to be 128. So I'm just going to write 128 like so. So I'm just going to comment so that you get to understand. Then we're gonna have this output features, right? And we're gonna divide it by the length of LoRa. So this is gonna be 384 divided by, it's gonna be 3. So this is gonna give us 128. Then we multiply this by uh, 2. So this is gonna give us 256, right? It's gonna be 256, and we're gonna project these to LoRa rank. So this is gonna be 2. So that's what this code does. But essentially, you can think of it from that paper that we saw. It's like that. It's like those, like those small matrices, like orange matrices. Yeah, that's how we can think of it. But in this case, because of we have to group like them in a query, key, and value, this is why we're doing them like this. Okay. Then we have the scaling factors, which we spoke about. We're gonna take the LoRa alpha divided by the by R. Then the weights is going to be required because we know this that we do not have to update the weights of the pre-trained model. So this is reasonable to do. Then we have this self dot weight dot new zeros. Then we're gonna pass the output features, right? Then we're gonna have this view, which is gonna be the length of enable LoRa. Then we're gonna say PyTorch. Think for the last dimension. So how will the dimension look like? Because of we passing here, I think it's gonna be what did he say? We said 384. So we reshaping this to length of 3. So this is going to be length of 3 by 128, like so. So we're going to be having something like this, because this minus 1 simple says that we should figure out the last dimension. So in this case, obviously, if you multiply this, we're still going to get this, right? So I think that's okay. But to explain the intuition why we're doing this is because you can think of like we can think of like we have a matrices, right? And we want to set the key to 0. Then we wanna set the values of the other matrices, like probably query or key to the actual values. So in this case, you can think of what we're trying to do is that we have like three matrices. Maybe this is going to be 1 1 1. Then the second matrix like this, we want to set this probably to 0 0 0 0. Then the third matrix like so, we want to set this to 1 1 1 1 1. So that's what we do in this case. Okay, hence here we're gonna say LoRa dot index, because of we passing the enable LoRa, which is a list of boolean, right? And we're gonna set this to be equals to true. So you see what this does. Where there is true within this, it's gonna be set to true because of we have this dimension. Okay, so that's fine. So you can think of like we have something like this, but instead of 1, we have true. Then because of this was initialized with zeros, so where it's not true, we're going to be having zeros. I hope that makes sense. Then we just apply LoRa.index.view minus 1. So this is just going to take our dimension to where we were. I think it's going to be 384, because we are saying that uh, Python should figure out the dimension for us by writing minus 1. So we are coming from this two-dimensional matrix, and it's gonna like try to multiply this 3 by 128 to give us this 384 dimension. Then we have this reset parameter function. I think this will be familiar with us, because we said that this the first matrix of the LoRa matrices, we're going to initialize it with random Gaussian. Then the second matrix, which is LoRa B, is going to be initialized to 0. This is to ensure that when the weights update at the start of the training are set to 0. Okay, then we have this 0 pad, right? So don't forget this self LoRa, what we just did here, because now these are going to become uh, you're going to see why we had to do that. Anyway, we're gonna be having the input, so we can think of this input as having the dimension of 64 by 64 by, we can say here it's going to be 256. So assuming that we want to probably apply the LoRa on probably, let's say, query and key. So this is what we're going to have. Then these dimensions are going to be representing a batch by sequence length by embedding size. Okay, then just keep track of this for now, so you're going to understand why I have to explain this. Just an example. But anyway, we have this x, which we're going to transpose the first and the second dimension. Then we're going to create this matrix, which is going to be called result with zeros. And uh, this is going to be made up of this, the first two, because of we saying all the way to minus 1. So it's going to be 64 by 64. Then we're going to be having the self output feature. So we can say this is going to be 64, right, by 64 by we said that the output should be 384, so that's fine. Okay, then we say that result.view minus 1, which is going to be self.output features. So here we're going to have 4000 96. Yes. Then it's going to be the output features, which is going to be 384. 384, like so. Then what are we doing here, right? You still remember this? It had 384, right? And we have 380, we have 384. So this here, it's gonna be holding, like it's gonna tell us like all those true and false. Don't forget that. So how we can think about this is that we are saying that whether it's true, we want to assign it to this, right? And whether it's false, just assign it to zero, because of anyway it will stay to zero because we're not gonna assign it to anything. So now we're gonna take x and we're gonna reshape it to this dimension here. So it's gonna be output feature, which is gonna be 384 divided by 3, because of the length of this is gonna be 3. Then we multiply this by 2 because of there's only two true inside that. So it's gonna give us 250 something, 256, I think, yeah. So we assign those values to these results, right? So which makes sense. So you can think about this way. So we are saying that we're going to be, because we know that the values which are not zero inside here, they are 256, right? 256. Then they're going to be assigned to 256, right? Coming from this x. Then the key or the value which was on zero is gonna be assigned to zero, because that's what we did here, right? I hope I'm not confusing you, but you can think of it that way. But the final output, or the final dimension that we're supposed to be getting from here, it's gonna be because of the dimensions have not necessarily changed, right? So it's gonna be the same. It's gonna be 4096. It's gonna be 96 by 38 384, because of nothing has changed. We just said that where the columns are true, we want to assign them to this, but the dimensions have not necessarily changed, right? So this is where it's gonna get interesting. So we're taking the results and we're gonna reshape it to this, which is gonna be 66 by 6. So it's gonna be, the dimension here is gonna be 64 by 64, because of we are taking the dimension of x, which is gonna be, I told you that it's gonna be 64 by 64 here, right? Then we're taking the self output features, then this is gonna give us 384. So it's gonna be 384. So what are we trying to do here? What is it that we just did? So I like this explanation from the lightning team. I'm just going to copy it and paste it here so that you get to understand. So what we just did is that you can think of it as this is what we did. Where there's query, we just like setting it to x, right? And where there's key, we're just setting it to 0, because we don't want to apply LoRa there. Then where there's value, we're just setting it to this, to the weight change. So that's what we did. So I hope like it kind of like makes sense a little bit. Yeah, if it doesn't, sorry if I confused you there. But anyway, let's continue. So this is going to be the train function, in which we're going to have to be matching the weight of the pre-trained model against the LoRa matrices, right? But not all the time we have to do the merging, because as you can see, the mode could be false. So sometimes it's just a simple matrix multiplication, but we will get into that and you'll see how it works. So explaining if we have to match the weights, what we'll have to do is that we need to apply the LoRa logic, and we're gonna get this delta weight. And we need to add these weights as shown in the diagram in the paper to the pre-trained weights. But when we do that, we just need to make sure that we scale these weights by multiplying the delta weight by the scaling factor. Okay, so how this work from an example perspective. So we said that LoRa A, which is the first matrix, is going to be having, I think we said, let's just go up. I feel like if we look into these dimensions, we understand much better. So we said it's going to be 4 by 128, then this is going to be 256 by 2. So I'm just going to scroll down and do that, which is going to be 4 by 128, 128, yes. So we are adding a new dimension here on squeeze, which is going to be 1. So it's going to be, actually we are adding a new dimension at the zeros position. So it's going to be 1 by 4 by 128. Then similarly here we are adding the new dimension, but at the last position. So the current dimension is 256 by 2. I hope you still remember this because we did explain how we got those dimensions. Then this is going to be 256 by 2 by 1 because we added a new dimension using the unsqueeze function at the last position. Okay, so we apply these transformation, and these are it's gonna apply the dot product between the two matrices, and we're gonna be end up with, I think it's gonna be 1 by 250 256 by 128, which makes sense because of uh, the output of LoRa should be having the embedding dimension similar to the um, pre-trained weight data, right? So assuming that the pre-trained data has this dimension, so it's going to be, I'm just going to make an example, which is going to be 384, right? 384 by 128, which is going to be the embedding dimension, right? So here it's going to be this because of we only catering only for two, I think it was query and key, so that's why we have 256 by 128. Then what we're going to do here is that we're going to be um, multiplying the delta by the scaling factor, and we're going to add this to the weight data. But the point here, just to kind of like take a step back, is that we are literally still trying to, we are literally matching the weight to the weight pre-trained weight, so we can think of like we are making some sort of like update. Anyway, the this output here, actually, sorry, I think this is gonna be 256 by 128 because of the squeeze function here. It's gonna get rid of that, the first dimension. So this paired function here, after we multiply the delta by the scaling factor, so this zero paired here, it's gonna try to ensure that we have the similar dimension as the weight pre-trained weight data. So it's gonna pair the dimension here from 256 by 128 to, I think this is gonna be 384, right? Because we need to take care of the missing the last dimension that it was missing, so it's going to be 128. So now when we add between the weights, we pretty much have the same dimension because of it's going to be 384 by 128, and also here is going to be 384 by 128, so we have this pretty much the same dimension. So that's that. Now, the function that we just applied, it's actually similar to this, so it shouldn't be hard to grasp. But anyway, this is kind of like shows what I was saying is that if we already have meshed, we just want to have a simple matrix multiplication between the input and the weight, and that's it, right? But if we haven't meshed, essentially we're gonna take the input and we're gonna pass it through the pre-trained weight. Then we're gonna add the result to the result of passing the same input to the decomposition matrices, and we're gonna add these two up, right? So it's the same thing that we did in the pseudocode, whereby we have to have a forward pass by taking the input and multiplying it by the pre-trained weights, and doing the same thing by taking the input, multiplying it by the LoRa matrices, and then you add the results up, right? So in this case, this is how we do. So we already know the purpose of having the zero paired, because it allows us to make sure that the dimension of the pre-trained weights matches what we have also with the LoRa matrices. Then this is also known why we needed to apply the scaling so that we can balance the knowledge between the two results. Okay, then when we're done, we're gonna return the results, and this is all it is to this, right? I hope I didn't kind of like confuse you that much. So this is gonna be mark only LoRa as trainable. So yeah, I think we also covered this in the pseudocode as well as the paper, in that we just needed to make sure that the LoRa matrices are the only ones that um, will be trained as we're going to be coming to this file, right? So then the pre-trained weights are going to be frozen. So yeah, this is the code here. I think it's self-explanatory. I'm not going to get into it that much. But anyway, I think this is all it is to this. I'd like to cover the LoRa fine-tune code, okay? So we have this main function in which we're gonna take the data directory. We're gonna take the directory of the pre-trained model. We have this output directory, which is gonna be where we store the fine-tuned model using the LoRa technique. And the thing about LoRa that I like the most is that you can actually store the decomposition matrices, which could be few megabytes. So unlike using what we call full fine tuning, whereby if you're fine tuning something like GPT-3, then you were gonna have to store like 175 billion parameter of the model. Like, so that could be quite expensive in terms of storage, right? We have this fabric here. So for those who don't know, fabric essentially is a technique which essentially enable us to accelerate PyTorch Lightning inference code. So it kind of like encapsulate these complex distributed systems functions, like things such as deep speed, and I also think from PyTorch they released their FSDP. So it makes it very, very easy for you to kind of like bring all of these distributed training technique into one thing. So you see here, you can pass all of these precision as you wish. So that's the cool thing. Then we're gonna have this function which is gonna load the data given the data path. So this is gonna load the test and the train data set. Where's this function? Yeah, this is it here. So it's gonna load the data and it's gonna return the train and the validation data set like so. Okay. Then we have this Llama config. So I don't know if you still remember from the previous videos, we covered this, in which is gonna enable us to get the Llama model, right, that we want. So this is also specified within the model.py file. Then we have this max sequence length, and also this is specified as a block size. Here I think they just they're gonna be using 256 as an example. Okay. um, where we have here, in which we can load the state of the model, right, given the checkpoints. Then we're gonna use this function that we spoke about, which is gonna be marking the trainable parameters of LoRa to be trainable. Then the pre-trained weights are going to be frozen. So that's that. We're going to be using the Adam optimizer. This is quite known optimization technique. Then we call this function with all of these parameters, which is going to do the training. Then when we're done, we're going to save the model uh, right within this path here, like so, right? Pretty cool. So here we can think of this mix max eta as a epoch, if I'm not mistaken. Yeah, this is how it's they define it, right? I saw like someone asking about max iteration on the, I think it was on the, I'm not sure, but I remember on the repo. I forgot what was the question, but I think some people were probably confused how this was defined. But anyway, if I after finishing this video, I'll probably link the link. I'll link the repo so that you guys can check it out. Anyway, we're gonna pass the train data set, and we're gonna try to get the batch. So we have this input ID and the targets. So this batch here is gonna be this function right here. which is gonna get the batch for us, right? So I think of it as a data loader. Then we pass the input IDs to the model. Then we get the logit. Then we apply the cross entropy loss function by passing the logit and the targets. Then we get the loss. Then we apply this fabric dot backward. We're gonna compute these optimizers, the gradients, right? But all of these things are gonna be happening only on the LoRa matrices. So this is gonna be quite much more efficient because of we don't have to keep track of the gradients for the pre-trained weight. So yeah. Anyway, I feel like this is quite straightforward to understand, obviously. But anyway, we save the weights and we just keep track of the metrics as we continue to train, and that's all it is to this. I know that this was quite fast to cover, but honestly, when it comes to training these models, I feel like the scripts are quite the same. If you watch the previous video, you'll see that we spoke about this. So it feels like repetition. So the key thing that I like to speak about is like understanding the core paper and trying to see how it getting implemented. Some of these things, as you'll see, like let's say you go to adapters, you see like it's just the same code. Nothing has changed. You're still using this fabric accelerator. So that's why I tend to cover these files at once. Then as we continue, I only focus more on the core algorithm or the core paper, the core logic of that, right? Otherwise, these ones we covered them in the pre-training step. But yeah, I think that was it, guys. I don't know what you guys think. I really appreciate it. I'll see you guys in the next one. If you did like this, which I assume you did because you watched it to the end. So yeah, thank you very much. I'll see you guys in the next one. Bye.